Good morning. Previously, we have determined the center of mass of a system of particles and the center of masses of objects of constant density by treating them as a small number of particles. Today, we are going to learn how to determine the center of mass of rigid objects with shape. In other words, objects of defined shapes which do not change shape easily. For example, we are going to determine the x-position center of mass of this right triangle with a defined thickness and uniform volumetric mass density. Before we do that, let's learn how to determine the center of mass of rigid objects with shape. In order to do that, Bobby, please tell me the equation for the x-position center of mass of a system of particles.
Flippin' physics.
The x-position of the center of mass of the system equals the mass of object 1 times the x-position of object 1 plus the mass of object 2 times the position of object 2 plus as many of those mass times position expressions as exist in the system divided by the quantity mass 1 plus mass 2 plus as many masses as exist in the system. Thank you, Bobby. I'm going to consolidate the notation here for this equation. In the numerator, we have the sum of each mass times its x-position, and the sigma symbol, the mass, and the x-position each have an I subscript, where I varies from 1 to the total number of particles in the system. In the denominator, adding all the masses of the particles in the system together is the total mass of the system.
That is just a more efficient way of writing the same equation.
Yep.
Yeah.
Cool.
Now what we are going to do is consider a rigid object with shape to be made of an infinite number of particles, which means we are going to be taking the limit.
Hold up, Mr. P.
Yes, Bo?
You can't just glide past that statement. I mean, you said, we are going to consider a rigid object with shape to be made up of an infinite number of particles. What does that even mean?
All objects are made up of particles. I mean, we basically did it before with the L-shaped piece of wood. We considered it to be made up of 2 objects instead of 1. Here we are just increasing the total number of particles to an infinite number.
And that means each of the particles must then be infinitesimally small.
Right.
Yeah, that's pretty clear.
Okay, I guess.
Yeah, Bo, it is a bit strange, but this is an integral.
Right.
Oh.
Right.
Yeah.
We are going to consider a rigid object with shape to be made up of an infinite number of particles, which means we are going to be taking the limit of this equation as the number of particles goes to infinity. The position of each of the particles is still x, and the mass of each particle is now identified as delta m. And as the number of particles goes to infinity, the particles get smaller and smaller, and the mass of each particle, delta m, becomes smaller and smaller until, at an infinite number of particles, delta m, each delta m is infinitesimally small, and we now call each infinitesimally small particle dm. This is, of course, as I mentioned a moment ago, an integral.
Cool. I love integrals.
Good. Now, as I mentioned at the beginning of this video, we are going to demonstrate how this works in practice by determining the x-position center of mass of this right triangle of thickness t and uniform volumetric mass density ρ. We will call it a uniform triangle, and please realize this uniform adjective is used quite often, and it means the object has a constant density. Okay, let's define a few things for our right triangle. The base of the triangle has a length a. The height of the triangle has a length b. Now, our job is to split the object, our uniform triangle with thickness t, into an infinite number of infinitesimally small pieces with mass dm. Those are going to have a shape of a rectangular box and be located a distance x from the left corner of the triangle, and that left corner of the triangle is located at the origin of our xy coordinate system. Again, the shape of dm is a rectangular box. The shape of the triangle is a triangle of thickness t. Notice those are not the same. The shape of the pieces which make up the object are often different than the shape of the object itself. So again, the shape of dm is a rectangular box. I do want to point out that I am only illustrating the two-dimensional version of these shapes because showing the thickness of both of these shapes would likely make the illustration more complicated and less understandable. Okay, x position center of mass equals the inverse of the total mass times the integral of x position with respect to mass. Notice the issue here is we are trying to take the integral of x with respect to mass.
You can't really do that, can you?
Not directly. You need to first find a relationship between x position and mass. For this, we are going to use volumetric mass density. The equation for volumetric mass density is rho equals mass over volume. But notice we have two different objects with the same uniform density, the triangle of thickness t and the rectangular box of mass dm. In other words, the volumetric mass density equals both the total mass of the triangle of thickness t divided by the total volume of the triangle of thickness t. And it equals the mass of the rectangular box dm divided by the volume of the rectangular box, which we will call dv. We can solve for the mass of the rectangular box dm. It equals volumetric mass density times the volume dv of the rectangular box, which we can eventually substitute back into our integral equation for x position of center of mass. However, first we need to determine more about dv. Billy, what is the equation for the volume of a rectangular box?
The volume of a rectangular box is length times width times height.
What then is the equation for the volume dv of this rectangular box dm?
The volume dv then is y times t times x.
Billy, y and t are correct. However, x is not correct. X describes the x position of the rectangular box dm in our coordinate system, not the width of the rectangular box. We actually have not yet identified the width of the rectangular box in our illustration. What do you think the width of dm in the x direction is called?
Oh, I see it. The width of the box in the x direction is actually infinitesimally small, and we call it dx. That is how the rectangular box is infinitesimally small. It has a volume of y times t times dx. It is basically an infinitesimally thin rectangle, which is why it has infinitesimally small mass. Cool!
Exactly. We can now substitute that volume dv into the equation for the mass of the rectangular box dm, which now equals volumetric mass density times y times t times dx. But do not worry, we can still do more with this. Remember, this volumetric mass density also equals the total mass of the triangle of thickness t divided by the total volume of the triangle of thickness t. Bo, what is the total volume of the triangle of thickness t?
It's just a triangle with a thickness measurement of t, right?
Correct.
So it's just the area of a triangle times thickness, or 1/2 base times height times t.
And what is that volume in terms of our variables for this triangle?
It equals 1/2 times the base, which is a, times the height, which is b, times the thickness, which is t.
Yes! And now we can substitute that back into our equation for the mass of the rectangular box dm. T, the thickness of the triangle, cancels out, and we get dm equals 2 times total mass of the triangle times y over the quantity a times b, all times dx. And now we can substitute that into our equation for x position center of mass. Now, I do want to take a moment to reiterate that the shapes and therefore the volume equations for the two objects, the triangle of thickness t and the rectangular box dm, are not the same. Again, those two volume equations are not the same because the shape of the object and the shape of the infinitesimally small pieces which make up the larger object are not the same. Okay, Billy, please simplify that equation and take everything out from under the integral which does not depend on x position.
Absolutely. The quantities which are constant with respect to x and we can take out from under the integral are 2, obviously. Total mass. Oh, and total mass cancels out. Y, actually no. Y does depend on where dm is located relative to the origin. In other words, the larger the x value, the larger the y value. So we cannot take y out from under the integral because it does depend on x position. But both a and b are constant, so those we can take out from under the integral.
Very nice, Billy. I will remind us all that our goal here is to manipulate this until we have an integral we can actually integrate. We are not quite there yet because we cannot integrate y with respect to x. We have to find a way to substitute something in for y which we can integrate with respect to x. Class, what are your thoughts?
Similar triangles.
Yeah.
We know tangent theta equals opposite over adjacent, so if we define the angle in the corner of the triangle at the origin as theta, tangent theta equals y over x, and tangent theta also equals b over a. Therefore, y equals b over a times x.
Actually, we could just use the slope-intercept form of a line, y equals mx plus b.
Using the letter b for y-intercept and the height of the triangle is pretty confusing.
Okay, y equals slope times x plus y naught.
Why not?
No, why not?
Oh, why not? As in y initial, which equals 0. Yeah.
Right. And slope equals the rise over run, or b over a, so we get the same relationship between y and x. Y equals b over a times x.
Which we can substitute back into the equation. B and a are both constants, so we can take them out from under the integral. B cancels out, and we have x center of mass equals 2 divided by a squared times the integral of x squared with respect to x. And that equals x cubed over 3.
But is this a definite or indefinite integral?
Definite integral. The x position of dm varies from 0 to a, so it is a definite integral with limits that go from 0 to a.
Right, and when we substitute in our limits, we get, well, a cubed over a squared is just a, so the x position of the center of mass of a uniform triangle with thickness t equals 2/3 a, or 2/3 times the base of the triangle.
Very nice, everybody. I have a couple of questions. First, does the thickness of the right triangle affect the x position center of mass?
No, it does not.
No. Second, does the height of the right triangle affect the x position center of mass? In other words, does the x position center of mass depend on the value of b?
Wow,
Still no.
It does not.
Correct, which is why I can take our right triangle and measure 2/3 of the distance from its corner and draw a line. Then I can rotate the triangle 90 degrees, measure 2/3 of the distance from the corner, and draw another line. And where these two lines intersect, we have identified the center of mass in the xy plane of this right triangle of thickness t. And assuming we have identified the location of the center of mass correctly, the triangle of thickness t should perfectly balance when I support it at its center of mass. And will you look at that? It does.
Yeah,
Nice.
that's fun.
Oh, and if we put the triangle into projectile motion, it will rotate around its center of mass.
Yep. So let's launch the triangle into projectile motion. As you can see, the triangle of thickness t rotates around its center of mass, and its center of mass traces out a parabola because it is in projectile motion.
The physics works.
Yes, it does.
The physics works. The physics works.
The physics works. The physics works.
The physics works. The physics works.
The physics works. Thank you very much for learning with me today. I enjoyed learning with you.